Hello, people. I'm just making a short breakfast while people show up. And then we'll start. The eggs are cooking. And because I'm back in Colorado, I have like a Colorado frou-frou stove that takes 1,000,000 years to heat eggs. So it is what it is. Just finished working on a Lexer for a small little toy language. Well, that is the way to start. That is how you figure it out. The 1,000,000-year egg, hopefully it doesn't take that long. Let's visit the eggs. Okay, they're just about done. But then I have to put the pastrami on. Okay, we'll start in a few minutes, but first I have to eat the egg breakfast. You know how that is. Boiled your last egg for 20 minutes. That doesn't sound good. What kind of eggs? I don't know. They're what you get when you put them in a pan and then let them cook. I don't know what you call that. Let them cook eggs. I think that's accurate. What are we saying about Snakebird? I think just as many people say something is bad without knowing why it is bad and just copy me when they make... Do other people make fun of Snakebird? I actually like Snakebird. Like, I have overall positive memories of playing that game, right? But it is Snakebird, you know what I'm saying? What's Lexer? Well, you can look that up. That's not a hard thing to look up. Just ramps up in difficulty quickly. I mean, yes, it ramps up in difficulty quickly, but I would also say it's kind of autistic in a certain way. And I don't mean that in an insulting way. I mean, Snakebird does not know how to communicate. And sometimes that's good in a way, but the problem is, it's too much. So it's too hard to deal with, right? Because it expects you, it's like your girlfriend who expects you to read her mind all the time and then do everything perfectly. It's like, yeah, you don't date that girl. You know what I'm saying? That's not a good analogy, but Steven Sausage Roll communicates more than Snakebird because this isn't about difficulty, right? So the problem with Snakebird, the developers didn't even understand what the problem was, right? So then they made this game called Snakebird Primer, which is Snakebird but easy, and nobody wanted to play that either. So the problem with Snakebird was not difficulty. How many puzzles does Sokoban have now? I haven't looked at the exact count in a little bit. What was the problem with Snakebird? I literally just said it doesn't know how to communicate. So the experience of playing a puzzle, it's like I say this all the time about my own games, right? But like a puzzle isn't just an arbitrary difficulty challenge, right? It's like, what is the puzzle about? What are you thinking about when you do it? What are the steps that keep you from solving it? And when you're trying to solve it, are you trying to solve sub-problems and think about issues that are coherent and relevant Or is it like random? And you know, okay, so Can of Wormholes is a little bit like this, right? It's no Snakebird, but definitely there are puzzles where the main point of the puzzle is something pretty interesting, but then it's also a little bit difficult on top of that, but in a way that is not relevant. Like, okay, like I got the idea, and that was a nice moment of figuring out the puzzle, but then, but I can't quite win yet because I haven't figured out some tweaky move maneuver thing that isn't the same, isn't in the same subject matter as the actual puzzle solution. You know what I'm saying? How do you manage difficulty in your own games? You make the games not ball-bustingly hard. So a puzzle isn't good if you need to solve different subproblems that are each interesting on their own, but not. No, you're jumping ahead and saying each interesting on their own. Like, is it really interesting that I have to figure out to flib before I flob? Maybe not. But it definitely helps if things are not non sequiturs, right? Like, imagine you're trying to read a story, and the first paragraph is 5 sentences that are all interesting individually as sentences, but they don't relate to each other very much. How good of a time are you going to have reading that relative to a story where the first paragraph is 5 sentences that are interesting as sentences and connect to each other and make sense relative to each other and lead one into the other, right? The second one is much better. The first one is how a lot of puzzle games are, though. You know what I'm saying? Lexer from scratch, not exactly in scratch. We'll start in a few minutes and I will explain what we're doing. I'm just finishing my eggs. I'm letting them digest. I'm not wolfing them down. Is it obvious to you when you're making a puzzle that it isn't communicating well? I wouldn't say it's always obvious. Sometimes it's obvious, but this is a skill that you build. Like, knowing how well you are communicating is a game design skill, and it's one that doesn't usually get taught. Like, usually when game designers get taught to communicate, it's by like popping up shitty help text or whatever, right? Or having characters say the thing, which isn't what you want to be doing most of the time, right? The way that I do it, when I make a puzzle, it's not just asking, does this communicate well enough? Because when I make the puzzle, part of what I'm designing is the experience that you have when you solve the puzzle. And part of that experience is being communicated at, right? Receiving the communication, like seeing, like, oh, this thing is on the screen. I see that it's there. I get that that signifies something important, right? So when I design a level, I'm designing that. So I usually don't actually have that much of a problem not communicating enough because I designed the communication in. And then sometimes people don't get the communication, but it's still an interesting mystery and puzzle. Like, because you see something, you're like, okay, I know that's super important. So that part of the communication is clear, but then it's like, why is it important? How could it possibly be important? Is the mystery, right? And that's the puzzle. And so if you design that way, you will have enough communication. It's just, you may want to like work on it and perfect it. Wait, if I already played your puzzle game, why do you want to send it to me? Do you try to add some redundant communication? I would not say I do that super often. Sometimes. But usually, I mean, there's different games are different, right? Which is why it's hard to generalize about this. So in Sokoban game, communication is often features of the level, in which case to add redundant communication would be heavily changing the level, and it would, I've got hiccups from the breakfast. It often would be unclear how to even do that anyway, right? So in that game, not too often. In something like The Witness, maybe more, because more when you're talking about the environment, less when you're talking about the panel puzzles. Because again, the panel puzzles are often very discrete and countable, and usually communication in that kind of scenario is very clear. And then if you were to try to add redundant communication, there's nowhere to put it, right? Without making the panel bigger, which is bad. In the environment, on the other hand, it's more freeform and analog. And so, yeah, you certainly could put redundant things. All right, we're almost done with breakfast. I might be in a chai latte mood, so we might do one of those soon, but not yet. The one you tried clicking on was the yellow bar outside of the tutorial area and it didn't work. Then you weren't. If it didn't work, there was probably something not right. About what you did. Don't blame me on that shit. In fact, I know exactly what was not right about it, and you would know too if you had understood the puzzles. Whatever happened to Golden Monkey Tea? We just did Golden Monkey Tea, like last week. Okay. So, that was the first one you tried. Yeah, that's a little bit of an, I don't feel like that's one of the better first ones, right? That one is sort of meant for later. There's probably some things we could do to elaborate on it to make it better for later. Let's do the thing. Let's talk about what we're going to do today. Wow, I really am going to need some caffeine. What do you think of puzzles that ask you something general and expect you to figure out the details on your own? You'd have to give me a very specific example of a puzzle. It's hard to answer a question that general. Okay. Here we go, people. No, you know what? So I just swapped time zones and I think my brain is lagging a little bit. So we're gonna rack up some tea before we go. Hold on. False start. We are, in fact, going to do Golden Monkey Tea with milk and honey, but I need to find the teapot lid. Here it is. All right. We got to also clean the optic on the Athena while the water boils. Did I bring the chair back from Florida or the lamp? No. I do have an identical chair at my office in Denver that I'm going to bring here in the meantime because I miss having a good chair. This chair is not good that I'm using right this second. Okay. Maybe just the smell of brewing tea will get my wake up flowing. Tried a golden monkey and didn't like it that much. Well, I mean, I often do just like an English breakfast tea with milk and honey. I mean, I don't drink golden monkey plain, right? I do it with milk and honey. That's what makes it extra good. There's lots of good teas. I'm a fan of the Harney and Sons Hot Cinnamon Spice, which I need to order a new pack of. All right. Let's actually finally get started. How's the background lighting? Oh. Ageism, unfair criticism from management. I haven't worked for anybody since the 90s. Like the mid-90s. Like 1995. Like you're asking questions that don't make any sense. Okay. So, what are we here to do today? Well, we've been doing these weekend projects for a few streams, and people seem to like them. So, what I've been sort of lining up in my mind ideas for just things that make nice, self-contained little things that we could do in a weekend. This is a weird weekend because I've been traveling. So weekend project might be today and tomorrow, which I guess makes sense because it's like a 3-day weekend for people who have jobs or whatever, right? So, one such idea that I had was as follows. For people who are making just editors and tooling for this programming language, right? One thing that you want to do is be able to parse the tokens out of a file, right? That helps if you're making an editor. It helps if there's just all sorts of reasons you might want to do that. Now, so far, when people want to do that, we don't provide any base lexical analyzer library. You know, I should explain like what actually this is, right? Because people don't know. All right, so what's a good example? Let's just go to, okay, here's a very small program. Let's just say x is 5, print hello. This was a test for a bug that we fixed. Okay. Let's even put these in opposite order. So what happens when you want to parse this, right, as a compiler or a tool or something, right? How does that work? And on the one hand, I tend to denigrate some of the abstractions that the so-called compiler community in academia has come up with. But there are some that are very useful and have lasted for 50, 60, 70 years, and that I certainly don't have a better idea for. And one of those is the way that parsing is made simpler, right? And that is that it happens in a two-stage thing. There's one stage called lexical analysis, right? Lexical analysis, which is done by a lexical analyzer or Lexer. And I can't type. That's why I need the T, everybody. This is the first stage of parsing, and it's just about taking the text of the program, the individual characters, and lumping it into bigger chunks that are still, they're like molecules, right? So if you imagine each character is like an atom, then the word main is kind of like a molecule of 4 atoms stuck together, right? And then the rest of the parsing just deals with these like molecules, right? So then there's like parsing, which is done by the parser. And parsing would just be messier and more annoying if it had to deal with character by character stuff. So it tends not to. Parsers in a programming language tend to deal with things called tokens, right? Which are these like molecule-like things that I'm talking about. And that's just a good simplification, because down at this level, you're only dealing with characters. And at this level, you're only dealing with tokens. And it just helps a lot. And there's not really any downside. Like, you know, usually when compiler people introduce some abstraction, well, and I end up not liking it, for example, it's because there are substantial downsides that tend to be ignored, such as, for example, it's really slow, or it only works so long as you want to factor things a certain way, but not as soon as you want to do something different, or it's just as much work to do this using a domain-specific tool as not. Actually, that applies to this situation, which we'll talk about in a second. But with this abstraction, it's just really clean, and it basically always is what you want, right? So I really have no problems with it. Now, the thing that I do have a problem with is in the compiler world, either in academia or when you go read a tutorial online or something, they will usually tell you, first of all, the big lie about all of this is that this task is super challenging and hard and you better not do it unless you're 5,000 IQ. None of that's true. The actual truth, compilers can be very difficult. They can be very complicated. But this is the easy part. Like, parsing is the easy part. If parsing is not easy for you, then you're not ready to do the rest of a compiler, because the rest is way harder. All right? And I've complained publicly about this book called the Dragon Book before that gets taught in academia. The Dragon Book is like 80 or 90% parsing, and they pretend like it's super, super hard, and they introduce all this super complicated things to help you with this ostensibly super, super hard problem. And they're actually just making it way harder than it is, right? And so anyway, if you're not reading the Dragon Book and you're reading a tutorial or something, they'll say, well, the way you make a lexical analyzer is you use a program like Flex, or I don't know. In the open source way, people keep making new programs to do these things, and they all only do 5% more than the previous program. So you just keep needing new ones and new ones. But so the original program was just called Lex, which is what I was able to use in probably 1989 or 1990 at college. And then later there was, you know, like Flex is an enhanced Lex. And then, I don't know, there's probably other stuff that people in chat could name. How do you need a book for a problem you can solve for yourself on a weekend by just doing it? I know, but like, dude, it's like an entire semester in college, right? Actually, Dragon Book was big enough that some schools would do it over 2 semesters, right? Like, there's no perspective. Now, there's a way in which this makes sense, which is the following thing. Early on in the days of computers, imagine a computer from the 1960s, or like hell, even the late 1950s, right? I'm trying to get chat up on another monitor so I don't have to have it. on the main monitor, and the web browser is, of course, not loading. All right, here we go. So those computers couldn't do very much. They were very, very underpowered compared to this computer that I'm using, or the ones you're using to watch this stream, right? And they were in the earlier days of figuring out how to solve problems with these computers. And so how to parse a programming language might have seemed very, very challenging, right? Because there probably was just like lots of ad hoc stuff and whatever. And so you come up with these formalizations. And you know, when you take a compiler class, you'll be introduced to all sorts of tedious discussion about LR parsing versus LL parsing versus LALR parsing, and you'll get taught about this whole stack machine way of parsing, which is stupid and nobody really should do it. But the reason they do it that way is because that was one of the formalizations that came up in the early days of computer science. And the thing is, what gets taught in school is whatever can be formalized. And once those things got formalized, the fact that they were kind of useless didn't seem to sufficiently bother anybody. Like if you knew well enough to know that they were kind of useless, you probably were not teaching, right? You were probably a serious programmer off somewhere. And you probably didn't have a PhD, and thus you wouldn't get hired. This is another one of the, okay, so we're just belting out the rants today without even sufficient time to complete the rants. In the early days of computer science faculty, how were these schools formed? They were formed by hiring the people who had been working on the most interesting projects in industry, because those were the people who had experience in this burgeoning field, right? If you go back, you can read this book, The Dream Machine, for example, that describes this in great detail, right? Like that's where the initial experts in computers came from. It didn't come from schools, because the schools, it was a new subject. The schools couldn't teach it yet. They needed to get the people who knew how to teach it, right? But what rapidly happened over merely 2 decades from that time is, you know, once the credentialing is in place, now who teaches? Well, it's people with PhDs. It's not people with practical experience in the field, right? And to get your PhD, what stuff did you learn? Well, you learned about LALR1 parsing, and so that's what you're going to teach, goddammit, right? So the fields, like every field like this, just gets corrupted super fast unless there are very strong like guardrails on it to prevent that from happening. You were told that parsing is the hardest part of a compiler and you should never write a parser yourself. Yeah, that's all. Whoever said that has zero practical experience. Zero. Literally every other part of a compiler is harder than parsing. Yeah, anytime, here's a general rule. Anytime in computers ever that somebody says you should never write this thing yourself, just stop listening to that person. Because, so it may be time saving to not have to write something yourself, but you should be able to. And it's interesting and fun. And in fact, keeping computers alive involves at least maintaining the capability to be able to replace these systems. Otherwise, it's just a dead mass that keeps getting added to, right? Somebody needs to be able to refresh the systems. And if that's not you, and it's not literally anybody else in the world, then we're at the mercy of the inevitable decay of things that were built by people who are now dead, right? Don't ever listen to somebody who says that stuff. All right, let me pour the tea, and then we'll go. Is it also true for cryptography? It actually is true. Anyone who tells you you should never write encryption yourself, don't listen to that person. However, it is closer to true in cryptography than anywhere else, which is it's very easy when writing some cryptographic code to make mistakes that make it completely insecure. That's true. But that doesn't mean, it obviously doesn't mean you should never write cryptography yourself. Because again, if you apply that statement to everybody in the world, now there will never be any new cryptography software. So obviously it's a false statement for someone sometime. And why isn't that you, right? So again, like people who say that kind of stuff, they don't tend to be the smartest people. I mean, that's a generalization that's mean, but I'm just going to say it. They tend to be like the mid-wit people who think they're smart. The smartest people are going to help you and encourage you. Well, not always. Sometimes they're curmudgeonly, but they're not going to like try to keep your head under the water so that you drown, right? They're gonna, I don't know. That analogy didn't make any sense. I need the caffeine. What your security professor says is don't write the crypto algorithms yourself unless you really know what you are doing. Yes, okay, that makes it a true statement. The unless you really know what you are doing makes it no longer a stupid thing to say. It makes it a good thing to say, right? Okay, but how do you get to know what you're doing? You have to play around in the subject matter, right? You have to work on stuff. You have to try making stuff, right? And the thing is, when you do that, you have to know, well, I probably made some mistake in this thing and it's probably insecure, right? Okay. Let's get back to what we were actually talking about. So, these two stages, pretty much any parser that you use today does things in these two stages because it's just so clean and works so well. And I would dare to say that anybody who writes a parser that doesn't have a lexical analyzer in front probably didn't know what they were doing. And there probably are some systems still in use. Like, I don't actually know, but for example, something like PHP or original Perl and stuff probably were not even factored this way. But this is a very good actual way to factor things. It's a good design. Tickle definitely is not factored this way. It doesn't, I don't think. It wasn't originally, back when I used to mess around in the Tickle source code. Okay, anyway, but most things, if you're writing your own programming language today, you want to do this. Now, so both, to support people in this language who want to use this language to mess around making other languages and their own stuff, and also just to help people with tooling, I was like, hey, it'll be cool to just make a module that people could import that does lexical analysis. But again, I don't want to make a general tool like, Flex or something, because I don't think that kind of tool is very useful. Like, something like that forces you to use some domain-specific language just to generate code that's easy to write yourself. And the fact that it's being generated makes things inflexible. It makes them dependent on tools. It makes it less expressive what you can do. And interfacing between that code and the rest of your code becomes more difficult. Like, just all of these things. But an easy thing to do is to just give people a working Lexer that lexes some language. And then if they want to modify that source code, they can, right? They can just screw around with it, make it lex something else. And then I was like, well, if we give people a Lexer for this language, they can both use it as a starting point to do other stuff. But then also if they want to do tooling support for this language, then that'll help them, right? And now if I'm going to do lexing support for this language, what better way to do it than to just start with the C++ lexer and translate it over, right? Because that way it'll match exactly what the compiler does today. I mean, of course, we could make a bug. Of course, they could diverge accidentally over time. But as of today, it would exactly match what the compiler generates. And that's useful for tool people. And in the long run, it actually helps us move a little bit toward getting the compiler out of C++, right? Because a lexer is a very self-contained thing. Okay, so we just said parsing is a two-phase thing where you generate these tokens and then you parse the tokens, right? But you could just run the lexer on a file and convert it to a stream of tokens and print those tokens, right? And so there's a way in which it's a self-contained piece of software that you could finish and verify that it works and then not worry about it, right? And then that part is checked off the list. Now, it's not that useful of a piece of software in absence of somebody who wants to use the tokens, but it is a thing that can be done in a self-contained way, and that's very helpful. Okay. So, we're getting raided by the strain people. Don't bring your disease over here. Don't make us get viruses. I hope your stream today was good. I'm glad you were rating me at a decent hour. Although maybe it means you were up all night. I don't know. Okay. Anyway, so what I'm going to do, this first stream is going to be a very smooth brain stream, which is fine because, like I said, my brain isn't on full. We're just going to copy over the C++ code, and we're just going to start converting it by hand. And we probably won't finish even during this first stream. But I would rather do that than some kind of automated conversion, A, because quality level ends up higher. And B, it allows us to revisit design decisions and say, would this certain kind of thing be more idiomatic or cleaner or shorter or easier to understand if we did it in a different way in this language as opposed to how it's being done in C++, right? So you're going to go touch grass. The grass might have viruses. All right. So I'm just going to go to the Lexer. Now, it's also the case, way back when I first wrote this Lexer, it was more of a C++ object with methods, and I demethodized it a while ago because I converted away from the Methodist Church. So it's already a little bit more in a friendly way for us. Why do we have weird characters in here? Raphael puts these triple dots in. That's probably what it is. He puts these European ellipses in, and Emacs is like, that's a European. All right, so it's about, I'm down at the bottom of, I got to turn off my trackpad. Hold on. Trackpad, I was on an airplane, so I had to turn it on. So we're about 2,000 lines. It'll probably get a bit shorter, but that's about what we're looking at here. I can do a pass over it. We can just sort of explain what it is and how it works before we do the conversion. All right, so here's how it works. A lot of tokens are simple. So if you look at just even this text here, right? A semicolon is a token, right? An equal sign is a token. Because a token is basically, the definition of it is whatever is convenient for the parser to handle, right? And so an identifier is token, like a token, because like you don't want to just look at the letter M in isolation if there's another letter after it. You'd rather just have the whole name of the variable. That just makes it easier to deal with, right? Comments tend not to be tokens. We're going to drop them, although we might, as an added feature in a later stream, let comments be tokens if you want them. It'll be interesting to think about how to do that, because it's actually annoying for the parser to have to say, if there's a comment everywhere, ignore it. But you know, sometimes if you're processing files and re-outputting them, you want to know what all the comments were, right? So just having some way of dealing with that would be good. Okay, anyway, so a lot of tokens are one character, and we already have, if you want an integer that stands for every token, which is what we want in this kind of design, then the one character tokens are already their own integer, right? So like equals has an ASCII value, semicolon has an ASCII value. And so for things less than, 128, they already have ASCII values. Now, not all of those are valid tokens that we're going to pass. But we'll just ignore those values. So anything less than 128 is, yeah. And then these are 4 tokens for things that have ASCII values, but I just decided to give them different names, which is why they're here. Whether we keep that or not, I don't know. The reason I did this was because it's a little bit of an abstraction. Like if you want to change how you spell bitwise OR, then if you give it a name, then you could make it a multi-character token later, and the parser code wouldn't have to change, right? So, okay, then after that, for anything that's not one character, you don't naturally already have an ASCII value for that. So like plus equals is 2 characters and so forth. Triple equals is 3 characters. And then there's other stuff, like a number could be many characters, a string could be many characters, and so forth. And so this is just an enum that gives these values. I started these at 256, but probably will bump them down to 128. It actually doesn't matter for the numbers to actually match the compiler between these 2 implementations, but we'll probably make them match. Anyway. And then we bump up to 500 here for, these are, like later in the compiler, there are functions where you say, what's the token for this operator? Like the inverse operation. And sometimes you want fake tokens for that. And that's what these are. End of input, of course. When the file is done, you can tell the parser that by sending it an end of input token. That's just an old trick, right? Hold on. I'm having a coughing time. Okay. Is allowing Unicode a crazy idea? I mean, that's sort of orthogonal to this decision. Because, like, I think what you're saying is, would you want to have a bigger integer range for single character tokens or whatever? And the single character tokens is just an optimization guide. It's like, it just lets us not have to declare 50 enum values for things that are single character. That's all that does. If you wanted to do that for a wider integer range, you could, but then your other guys that are not single characters would have to be like elsewhere in the range, and it becomes annoying, right? So anyway, that's what that is. So here's our struct that we pass through. It's got numbers for what is the starting line and character number, and those are always set. And then it's got what is the ending line and character number, which are like sometimes set. And to be honest, so these values we end up putting also in the parser, right? We copy them over. And long term, like the thing about parsing, the way it's traditionally done is you build this thing called the abstract syntax tree, which is just a tree with a node for each type in your language. And on the one hand, just like this lexing abstraction I said is super useful and effective, abstract syntax trees are also super useful and effective. I don't have a better idea for how to do it right now. However, trees are also pretty bad on modern computers. They're bad for memory locality reasons, and they also just take a ton of memory, like a freaking ton. Like just to say, if I have a buffer and I just say x equals 5, the syntax tree for this is going to be some node for equals and some node for x, right? And some node for 5, and they're going to, right? And that doesn't maybe look too bad until you realize each of those nodes is probably like fucking 200 bytes. And I'm not even exaggerating, right? So it's like 600 bytes to write this thing where if you delete the spaces, it's 4 bytes. Okay? And this sucks. And it's why a lot of compilers are slow. It's not the only reason those compilers are slow, but it's one reason. And so your last compiler had a single array for the tree. Yes, that's a whole subject we could talk about another time. There's certain constraints, of course, you have to do if you're going to pack stuff into an array. Anyway, I am not very happy with the fact that our representation of the program is syntax tree based and would like to come up with something else. But various array schemes that I would come up with always have disadvantages as well. So I'm just trying to figure it out. But anyway. And you might ask, well, why is it frickin' 200 bytes? And well, just the location information for that token, 4, 8, 12, 16 bytes before you even have any useful data that you could do anything with, right? So it goes up rapidly. Binary tree is enough? Well, no. I mean, a lot of your nodes will want more than 2 pointers off it. So if you restrict yourself to a binary tree, now you're kind of obfuscating your tree, which has consequences. Like certainly you can. Yes, you can represent any syntax tree as a binary tree. But it's not a good idea necessarily. Okay, so here's a union where, depending on what this token type is, maybe none of this data is used. Because if you say this token is a semicolon, semicolons don't really have any more properties that we care about, right? It's just a frickin' semicolon. What are you going to do with it? Well, you just know that there was a semicolon there. So you don't really need any more information. But for some types, we do. Like if it's a string, what's the contents of the string? If it's a variable, right, then the type of the token is going to be like identifier or whatever we call it, right? And then this will say what's the actual name of the identifier. If it's an integer, what integer is it, right? If it's a float, what float is it? Now, like I said, a lot of tokens don't need this. If you say plus, you don't need any of this. So you might, if you were trying to be super tweaky optimized programmer, have a whole tree hierarchy of different token types, right? And subclass them because the semicolon token does not need these members, so it should not have them, right? But here's the thing. That's not optimal at all because it makes your program a lot more complicated. It also makes allocation of these tokens more complicated. Like your parser doesn't need more than a small number of tokens at a time. And so you can just have like 5 of these structs laying around and recycle them as you give them to the parser. And so you want them to be the same size as each other so you can treat them interchangeably. So you don't have to think hard about what kind to give someone, right? You certainly don't want to heap allocate tokens because they're so short-lived. You just give them and go. Now there are, so the way that we do it is we do a pass over the file and we lex and parse sort of at the same time. You could imagine lexing completely separately and generating a stream of tokens that's consumed separately, in which case they would live a little bit longer, but you still would want them to all be the same size. Like it's just not worth, like enough of your tokens are numbers and strings and whatever that you just are not going to save anything. Like the amount you're going to lose by heap allocating different sizes of tokens is going to cost more than the amount you think you're saving, right? And this is a thing to just understand. Why don't you just store all the values of the tokens as a string? Because the value of lex, the whole point of this layer is to produce data that is very convenient for the parser. If you just give the parser strings, you're not making things very convenient. Have you seen Eli Bendersky job ob pick parser? I can't read what you're typing. So probably not. PyC parser. No, I haven't seen that. There's lots of parsers in the world. You wrote your parser as an ad hoc relational database, so your nodes were very compact. Yes, it was also a slow parser. Okay. So anyway, this is other data. And dude, I haven't even tried to pack things. So like here, I have a Boolean. And like literally this could be in value flags probably. It's just, I didn't want to go audit value flags to see, because people might have been using this for other, yeah. So I just tacked a Boolean here. This should be a flag, whatever. We'll probably do that kind of cleanup in this project, right? Token scratch buffer, that really shouldn't be there. Wow, that's 512 bytes. Yeah. I don't remember what this was for or why I did this, so we're going to look at that. I certainly said it's kind of lame. I don't know why I put it on the token. Okay. So because we're in C++, we have to pre-declare everything, like we're going through customs. Okay, now, like I said, this interface is about providing things that are convenient for the parser, right? So what's convenient? Well, let's go ahead and delete this old commented out code. What's convenient? Well, very, very often, the most common thing the parser wants to know is what's next in the file, right? And if we already know what's next, because you might have peeked at it already, we just give you that, okay? Otherwise, we say make a new token, which is where all the complexity is, right? And then we say, hey, we've got another token, and we return that one. So this is just what the compiler calls all the time, right? Get last token, I don't know that anyone calls this. Let's see who calls that. This seems like it might just be old. Get last token. Parse elsewhere information. Okay, so this is like the token before the current token. This is like a token that was already consumed, I think. Maybe that's not true. I'm going to have to refresh my memory of how this works. This is something we don't use very often. It certainly doesn't need to be inlined, given how little it's used. So let's look at this one. If there's a semicolon, this is just a special case of helping people and saying, look, we expected a semicolon. So we're reporting I don't know why we're re-getting this, because it seems like this is the right token to report. Certainly there would need to be a comment here. Report error at the end of the previous token. Yeah. So I think this is like a token that we already accepted. So if you go into like more formalized parsers, right, especially these stack-based parsers, there's an idea of like what tokens have been accepted, which sort of means we made our decision of how we're parsing based on these tokens, so we don't really need them as much anymore, right? And then there's tokens that are not accepted yet. And so I believe this is like the last token we already accepted. Although when we do this cleanup, we will verify that and make sure it's documented more. Let me just show you what this data structure is, which probably isn't very good. So we have this thing, max concurrent tokens, which is 8. I don't remember why it must be a power of 2. We should explain why. Explain why, or better, just change this, right? Probably this doesn't need to be this way. Like, we are working on code that goes back to the very beginning days of the compiler. So quite a lot of it just might not be appropriate anymore. But anyway, so we have a cursor. Oh, it probably has to be power of 2 because we're wrapping it by bit masking the index, right? Like this is just a ring buffer that we mask probably. Okay, so we have a cursor that goes through. Num incoming tokens is how many things are going to be alive in the ring buffer yet, right? And so what this means is your parser can't really ever look ahead by more than 8 tokens. Now, you don't need that. I do some look ahead. I think the maximum amount that we ever look ahead right now in the parser is 2 or possibly 3 in a very rare case. But like almost all the time, you just look at the next token and you know what to do. Yeah, okay. All right, and then here's a function. Does this token start an identifier? Because that's something we want to call from our main loop a lot, right? And honestly, this is a slow version of starts identifier where we're leaning on the optimizer. Because like is alpha, I mean, you probably shouldn't call that. Is alpha, the implementation varies depending on your system. I think it's usually a macro these days, which means the optimizer has an easier time seeing that it's optimizable, but it's still, depending on how that macro is written. Let's see. This is a little bit of a diversion, but let's see what the implementation is. Okay, go to definition. Oh my God, dude. Okay, so because this is written by modern programmers, we're not going to be able to understand what the fuck is going on. Also, this isn't going to be very fast. So here's the thing. Here's the thing about alphanumeric characters in ASCII is their uppercase and lowercase are only off by 32 from each other. So if you want to know if something's alphanumeric, I just want a very readable table. Let's just see. This is not, okay, so we have A, capital A is 65, lowercase a is 97, right? Notice how these are parallel in two columns? The reason for that is because these are columns of 32. And these are off by 32 from each other, which means if you want to know if something's an ASCII character, first mask off the bit, right? You mask off the bit for 32, and then you say, is it between 65 and 90, right? So you do a mask and two comparisons, right? Whereas if you don't do that, you would have to say, is it between 65 and 90 or 97 and 122, which is like more comparisons, right? But as soon as you're going through some generic fucking system like this is probably a lookup table, which is probably worse than what I just said, because these days CPU instructions are free for the most part. I mean, they're not free, but they're going to cost you less than a lookup table. I don't know, very small lookup tables could be fine. Okay. This is a frickin' function for some reason. Like, why does all modern support code look like this? It's like you can't understand anything. Just like put the function. Anyway, this is, okay, by the way, this is one of the reasons why I wanted to write my own programming language, is because, okay, oh, here we go. Here's the functions you would have wanted to see. I guess these are old and deprecated. These are for the wide characters, right? Okay, but again, this is the slightly slower version. Yeah. Anyway, at least I can understand this. I look at this and I'm like, oh, I get that. Cool. Yeah, I see exactly. The rest of this code that's like nightmare size and like full of eels, like, yeah. We haven't even gotten to the actual implementation of this, which is probably not available to us because it's a function, right? Like what? Why do these people get paid hundreds of thousands of dollars? It's unimaginable. Wouldn't modern compilers figure out the intent and optimize it anyway? Sometimes. But there's lots of problems with that. Like now your debug build is even slower than your release build for no reason, right? Because optimizations aren't turned on for your debug build. Now the code's harder to understand when you look at it. Now it takes longer to compile because you're giving your optimizer more to do just to make your program bearable. Like all of these things have costs and people ignore the costs because they're bad at their job. Okay. Let's get back to should be in the shipped CRT sources. I don't have those probably. And I don't care enough to, I was just going to look if it's convenient, right? And anyway, okay. So C++, still, we're in the body. We've got some enum for parsing hex digits, right? I actually don't know what this is. Is this something someone else put in? Oh, this is, okay, this isn't what I thought. I thought this was for parsing hexadecimal numbers. This is for parsing Unicode escape codes. So in the middle of a string, we let you put backslash U and then some digits, right? And it's either an 8-bit, a 16-bit, or a 32-bit number. And so this here, these enums are just more about correctness checking. Okay, cache make atom. Okay, so early on in this system, we interpreted this conceit from, functional style, interpreter style things, where I don't know how much. So in Lisp style languages, you have all these things called lists, right? Where you have nodes pointing at other nodes. And you have things called atoms, which is things that aren't lists. And the way a lot of these systems worked initially was there was like a global table of all the atoms with maybe some specialized handling for integers and stuff, right? And then tokens, like variable names and stuff were atoms in the atom table, and in Common Lisp you can even like add properties to variable names, which is a pretty weird thing to think about if you're like a C programmer, but that's how it worked. So I kind of started doing things like that because that was like my education in history. The problem, and there are benefits to just having a global table full of stuff. Like if somebody uses the same variable name a bunch of times, you just point back at the text of that variable name. You don't have to reallocate it and have a bunch of copies. If you have two variables and you want to ask, do these have the same name? You just look at the pointer into the atom table, which is an integer compare. That's a lot faster than doing a string compare, right? However, this starts to fall apart in a multi-threaded system because you would end up globally synchronizing on the same table all the time, and that makes you really slow. And so now what we have is one table per Lexer, which makes things, you still get some of the benefits, but I'm honestly not really sure how worth it is. Because you can't really use it to compare anymore, because when you're parsing along, you might have identifiers within one parse tree that came from two different Lexers. Easily you can have that. And so you can't even use it when looking up variables anymore and stuff. And so I don't know, maybe I would structure it a different way. Maybe we'll do that in the weekend projects, etc. Okay. Eat character just advances some numbers about where we are in the input. This really is a lot of work to do per character. Is it a new line? Okay, do some stuff. yeah, I'm not sure that that's the best. In some way, it doesn't matter because the Lexer is the fastest part of the system anyway, and so it is what it is. But you know, I look at this code and I'm like, yeah, the fastest version of it probably is something different. Okay, peek next character. Just like the parser wants to peek at the next token, the Lexer often wants to peek at the next character because we want to figure out what we're doing when we're like parsing a number or something. Now, the way we handle files here is very different from the way traditional compilers would, because compilers were originally written back in the days when when files were considered big because you didn't have a lot of RAM, right? And so they were doing all this like file streaming, and you would like fgetc in here or some shit like that. And that's horrible and slow. But the thing is, you probably have, you know, 32 gigabytes of RAM, and your file that you're loading is probably, well, this is a typical file size, 2000. In fact, if you go to a modern programming school, they'll say this is a horribly large file that you never should have, right? Let's see how big that is in bytes rather than guessing. How big is it? It is 74 kilobytes. All right. So now let's do this computation. Let's round it up to 100 kilobytes because it's a bigger file, right? To be conservative. Why did I get two calculators? So let's say we have 32 K megs gigabytes. That's how much RAM we have. All right. We're going to divide by 100. Oh, shit. The precedence isn't what I thought. we're gonna manually, okay. 32 K megs gigs, all right, divided by 100 times 1,000, right? 10, 100,000. Boom. Okay, so I could merely, before using swap space, load 343,000 copies of this file into memory, all right? Now, that's not actually true because your operating system is probably using a lot of your memory. So let's just say we could only hold 10,000 copies of this file in memory because we're severely under resource load. That's still fine because we only need one copy of this file in memory to simplify our life, right? So what we do is we just load the entire file first, right? And then we just blast through it. And that simplifies our software engineering tremendously. You might think that it results in you being slower because you don't, you know, because you're not like lexing tokens in parallel with the reads from the disk. But with a traditional C API, you're not going to really get any parallelism anyway. Like the only way that you're going to get good parallelism out of that is with a modern, fully asynchronous API. And you would, like, to make that engineering worth it, you would, like, the rest of your compiler is so much slower than this that you'll probably never get to the point where this matters in speed. Because by the time this matters, your compiler is going to be so much faster than the compiler that this is right now, or anyone else's, that like, yeah, you just wouldn't care. Now, maybe there's some special application domain that is only lexing, and then you want max lexing throughput, and then you should think about that. But that is not what we're writing this for, right? Wouldn't mmap do that for you? No. No, dude. If you... There's this like meme in software engineering that like mmap is a fast way to do file access. It is not. It is not. Because you're just not in control of what's happening. Is the operating system going to prefetch this thing for you? I don't know. What time scale is it going to prefetch it on? How much is it going to give you, right? Okay, you've got to keep in mind, this Lexer, like I don't even know how many instructions per character it's going to be, but it's like not that many instructions per character, all right? So the throughput of a Lexer that's running fast is going to be like, right, remember you have a CPU in the gigahertz range, right? If you're using just one core, you probably should be getting somewhere in the gigabyte per second range, like just with a dumb loop before you're optimizing anything. I don't know, right? Whatever. Like, are you telling me you're going to use mmap and the kernel is going to somehow smartly swap in a gigabyte per second for you in the right way to keep your program running fast? No, obviously it's fucking not going to do that, right? So like, that's the thing is like people who come up with these ideas, they're not operating within a performance threshold. They just have never really written performance software, so they haven't even thought through these questions, right? Like, but again, so if you look at modern file APIs, modern APIs for highly parallel systems all basically look the same. They're all of the following form. Here's a small command packet telling you what to do. I'm going to pass this off to you. I'm not going to wait for you to do the thing. There's some way for you to tell me when it's done. I'm going to go off and do a bunch of other stuff, and then when it's done, I'll check. And then, for example, for a file access, when it's done, the data will magically be in the memory location that I gave you in the command packet because you put it in there asynchronously to the rest of the system doing things, right? If it's a network packet, it's like, well, I promised, like part of my sending you the command packet was a promise to keep that memory mapped and valid so that you could read it asynchronously and send it on the network. And now that that's done, I will unmap it, right? They all look like that. They don't look like mmap, right? Like IO urine. I don't know what IO urine looks like, so I'm not sure. Okay. Anyway, like if you had the documentation for the PlayStation 5 API, like that's the kind of thing I'm talking about. Anyway, we're getting off topic. Where does the myth come from anyway? I mean, the thing about most programmers is they hang out on Hacker News and talk about stuff instead of actually programming, right? So if you're hanging out on Hacker News talking about stuff and somebody says that's the fast way to do it, and do you want to be a smart programmer, you're like, oh yeah, I'm remembering now that's the fast way to do it. And then maybe even you go program that and it appears to work and you're like, great. But if you've never done the actual fast thing, or you've never done the first principles exercise of asking, how fast should I be able to do this relative to how fast this thing is letting me do it, you're not going to understand that that's actually quite slow compared to what you could be doing, right? And because most programmers don't spend their time programming, they never get to the point where they really try it. Like for real. Overlapped plus IO completion port. No, there is. I thought Windows had also released a new API that is this kind of new modern async thing. Didn't they? It's got some fancy name. Direct storage, I think is what I'm thinking of. I haven't looked at direct storage. I don't know. But I think it's trying to be that PlayStation style thing. But I haven't looked at it, so I'm not sure. Maybe we'll do that sometime for a weekend project. Anyway, for files this small in this kind of Lexer, we're not worried about getting that kind of parallelism because it's so fast to read this off an SSD is the point. So we don't care. Okay. So get hex digit, this is just a helper function for the parsing the numbers. It's like we're going to read a character. We know how many we want, so we just loop over this 8 times and look at the characters, right? Decimal digit, this is if we're parsing a decimal number. Oh yeah, this is for \d, which is a different. So \u is Unicode in hex, and \d, I forget why I did that. But it's basically when you want to put an ASCII character value that's between 0 and 256, 255, right? I don't remember why I thought that was good, because I forgot that was in the Lexer. Maybe we'll take it out. I don't know. Okay, these are just utility functions that do basic stuff. Unwind one character. We got rid of this input file thing. Okay, so we had that. I don't know why we put these in different places. We'll probably move them together. But, well, it's because one's in the header and one's not. But we had this question, can this character start an identifier? This one is like, can it continue the identifier? Can this character start a number? This gives us a new token out of that ring buffer that we can return. Classic min function. Okay, when you want to parse an identifier, the way you get to this is we ran through the main loop of the Lexer. We said, oh, this character could start an identifier. And so we end up here. And this is a SIMD version that like identifies what characters are valid. And I think we did this on stream a long time ago, although I don't know if we saved it. But we're going to comment that out for a while and just do this part, which is the slower style thing. When we're doing identifiers, we allow backslashes to be an identifier, so that's like an extra scenario, right? But this is just your classic loop where as long as the character continues the identifier, we move forward in our scratch buffer where we're just building up the identifier name, right? Let me just check, because this whole thing about, remember how we had this 512 character thing? I wonder if we're still using that. Yeah, okay. So we're putting it into token scratch buffer. Yeah. Maybe there's a better place to put it now. Okay, so for a here string, that's a thing where, you know, you say string, and it's like a shell script style string. where you say explicitly what is the tag that ends the here string. And the reason you do that is so you don't have to worry about what's in there. Like you could put quotes in there or whatever. As long as you know some sequence that you know is not in the here string, which is a relatively easy problem. Okay, so I don't know if I'm going to belabor what actually happens here, but it's like, this is parsing the beginning of it where we're looking for what's the identifier. We're actually using our own Lexer to parse an identifier here. And then we're eating white space. I'm surprised we don't have a utility function for this, but maybe we don't do it enough to make a utility function. Because again, like skipping white space, if you SIMDize that, it could be super fast. All right. So now we're reading the actual string. So we just read through and we look for, you know, what is the identifier that ends the here string. And if we didn't get that, we just go to the next thing and keep going. Okay, now this is an option. This is a thing where we compose the result string. We're calling malloc here, which is not super good, which is something we might want to think about. We could get that from a pool or something. Depends on what our requirements are for the life of the memory. This is some code that was modified by someone else after I wrote it, but what it's doing is you know, we have an option on the here string that says we want, you know, Windows style \r_n every time, right? Because we don't, like, here's the thing. You don't want the contents of the here string in binary to depend on like the file format in which you read the file, right? This \r/n thing is one of these horrible, useless complications that wastes everybody's time on trivial shit, but we just have to deal with it, right? So that's that. If you didn't want that and we ever detected a \r, we have to go remove them, right? And there we go. I believe Raphael added that because initially I hadn't been thinking about that or punted it till later or something. And then we decided to get more serious about it. So this is actually a pretty long function to parse a here string, right? It starts at 252 and it goes to 481, right? So it's 230 lines, which if you were in one of these horrible programming classes that says all your functions have to be 10 lines, that's 23 functions to parse a here string. Have fun with that. Okay. Notes are things where you start it with an @ and I think we just parse until white space. I don't remember what that does. Let's see. We stop at white space EOF or semicolon. Yeah, otherwise we put, because we want notes to be able to have punctuation and stuff because we let you parse out. For example, we use hyphens in our notes to designate version ranges and stuff. Okay, so, all right, so now we're about to enter the keyword thing. Okay, so when you have characters of text that look like variable names, right, it is traditional in programming languages, in a lot of them, that some of these are keywords. Like the word if looks like a variable name, except we happen to reserve that one to mean if statement, right? This is very common. It's in that function, you check if the character is -1. What character code is that? That's EOF. End of file. Right. That's what we put in our buffer, which is also, you know, like, okay, so traditionally that's what the C, you know, F get C would also return you at EOF. We just kept that for tradition's sake, but honestly, it could be any value that is out of band of what you are normally going to process. Let's put it that way. Right. Okay. So anyway, this was a version that I did when I was like, okay, let's arrange. We have a lot of keywords. Let's just do a switch statement where we check the first character and then we call string compares on all of them, right? And meh, that wasn't that good. Instead, because we parsed out, so the way this works is you get something that looks like a variable name, and then you just see if it's a keyword, right? And because we first got the entire string of the variable name, we know how long it is, right? And so I do a switch by length. And I'm not sure why this is faster. I haven't looked at the output code, but it might just be that this is easy to turn into a table or a binary tree of branches or something, right? It doesn't totally matter because, like I said, the Lexer is really fast. But so we have these arranged by length. And then if you get a 4-character identifier, we just literally do this. And this is really stupid, but it works, right? We could then subdivide this by first character, whatever. Longer term, honestly, something that probably would be faster than this would be to maintain a hash of the identifier as we create it, and then just looking that up in a hash table about whether it's a keyword, right? But I didn't want to bother with that initially because, like I said, it's fine for now. Anyway, make ident or keyword, right? So we parse an identifier, and then we say, is it a keyword? If it is, we set the type. Otherwise, it's an identifier. Okay. Hex floats. This is when you say 0H and a hex code. We just, you know, we parse it out. It looks a little bit similar to, you know, so we had this different hex parsing thing. Where was it? At the very beginning here. This thing that gets hex digits 8 times. The thing is, I mean, I could have called this here. The difference is just this one, it's an error to not have a hex digit. And here, it just means we're done with the hex float, so it's valid. And it's like, do you want to make a function just for this? Maybe. But like, it just wasn't worth it, right? So also this is like factored a little differently between the two cases, and maybe that matters. Yeah, this is a little bit silly because because we're checking to see if we have the original thing here where all of these are going to produce values greater than or equal to 0. So yeah. Also here we could do our 32 mask trick to combine these. But that's only a slight win. Yeah. Anyway, like I said, the Lexer is already so fast. All right. We do some stuff where we determine the precision of the number based on the number of digits in the hex float. Okay. Now, make a number. We start when we see a numeric digit. And this one, you know, we've got to parse through what are the different formats. And again, this is like not trying to be super optimal. So like in the loop, so like we see a 0, for example, and we start parsing a number, and then we're checking for OX and OB and OH. But like every time around the loop, we're checking, as opposed to parse the initial character, then check for that prefix, and then go the main loop, right? And again, it's just because I wanted the code to be a little simpler. But yeah, if you wanted to maximize speed, you would pull this out of the loop. But yeah, we have 3 different. You can hex number, you can binary number, you can hex float. Underscores are legal in our numbers. If you hit a dot, then it's probably floating point, unless you get 2 dots in a row. Anyway, so this is all just like blah, 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 right? Here's literally our 3rd time that we parse hex numbers. Or Lex hex numbers. And then, you know, I don't want to describe every tweaky detail, but there you go. And then if we got a decimal point, then, you know, it's a float, and we do some float stuff here. And again, we figure out whether it should be float 32 or float 64 based on what the input numbers are, which again is this mildly questionable idea. Okay. Anyway, that's a pretty complicated function as well. Let's see how big that is. That goes from line 759 to 1045. So it's 290. It's even more than here strings. Okay, make a string constant. For example, if you see a single quote, again, we do a loop. This is, okay, part of the reason why I say Lexers are so simple, I guess we did \f and v at one time and we don't anymore. Lexers are pretty simple because everything you do in them is basically of this form. It's, you're in the main loop, you see some character that indicates what you want, like, oh, it's a quote, so we're going to parse a string now, or oh, it's a number, so we're going to parse a number now. Lex a number, right, whatever. And then you just call a subfunction that does that thing, right? And that's what all these functions are that we're stepping through, right? So this is for making a string constant. It's like, okay, cool. You know, what, like in C, you can have special, like a tab character, \r, new line, right? \0 puts an ASCII 0. \E is escape, etc., right? So we just do these things. And it's just, it's a loop. It's just a really dumb loop. It's just like anything. And then, oh, so for some, like I said, you could say \d, and then we let you put 3 decimal digits. And I just very smooth brain say, is there 1 digit? Is there a 2nd digit? Is there a 3rd digit, right? And then just do the math. rather than parsing. And we could have called our own parse number there or whatever, but it's like, it's a Lexer, right? And this is just how it works. Why do you eat character after every if condition? Because that's how we move the character cursor forward. You'll notice it's not always after. Like, we do different things. Anyway. And that's why, so, you know, when you talk about the basics of a Lexer, right? And why do I say it's so simple to write one? It's because of that. It's because it's all just first write a function that cranks through the characters to do a specific subtask like a number or a string or whatever. And then just your outer loop has to know when you call that function. And then the rest of the code is all whatever the specific weird things are that you want to do. Like, what are my escape codes in my string and whatever, right? And now the thing is, all the things that try to make this easier, they give you some, you know, domain-specific language that you have to learn that's like, oh, this is our little Lex language or whatever. And you could put regular expressions and say what to do with things. And then the problem with all that is it doesn't buy you very much. And it limits you in certain ways. Like it sounds convenient to say, here's a regular expression for what the numbers are that I accept, right? And it sounds seductive to just want to write that. Never mind that regular expressions are inscrutable and hard to get right. After you get them right, they're concise and that's nice, right? But then it's like, okay, now we want to have underscores at arbitrary places in our number. And it doesn't advance the numeric value. So you kind of need to have some kind of loop situation anyway. Or like, we're parsing our string. Now we want to go do all the escape codes and whatever. Well, the regular expression isn't really going to help you with the escape codes. Like, any way that you would translate this escape code into this numeric value, any way that you do that with a regular expression is going to be like messier than if you just frickin' did it, right? So, and slower. So the thing about that is, it seems seductive and appealing as long as you're doing something simple. But as soon as you have a lot of specific things, like, or I want to set all these flags in here based on the number of hex digits that I parsed, right? Was it 2 or 4 or whatever? And in regular expressions, you're going to end up making redundant overlapping regexes to like detect the number of digits or something, right? Or I don't know, it depends. Depends on what primitives you're given. Like in Perl, you maybe can frickin' do it. I don't know. But the point being, you end up wanting to do all these things that are not strictly the regex part. They're more like reasoning about what the token is. And those systems just don't help you with any of that stuff. It's just like the same code that you would write. So just write it, and then you don't have dependencies, and it's faster, and you can change it more easily, right? That's all. Will we make the Lexer module parameterized? Parameterized based on what? What do you want the parameter to be? Okay, so for here string, we count the lines. Eat token. Okay, this is a thing that the parser calls a lot. And this is just like I said, there's a thing about accepting a token. Like, okay, we looked at this token, we did what we're going to do based on what we saw, and now we're going to move to the next one. That's what eat token does. So, although this is this is broken into 2 operations, you might imagine eat token and look at the next token to be the same operation, but I found that I often wanted to do them separately. So I just made them separate. Okay, check for equals. This is called, so if you see like a plus or whatever, is it a plus equals? This is just a convenience. You'll see down when we call it. This is just a convenience function. Eat input due to block. Okay, when you see the start of a block comment, you want to blast forward till you see the end of the block comment, right? So now, and that's this case. Here we check for starting another comment, and the reason is because we count this comment depth, right? Because often you'll just comment code that has comments inside it. And so we track the comment depth there. Okay. Eat until new line. This is just something we call at the end of lines. We have a SIMD version and then a loop that handles extraneous characters. And if you turn off use SIMD, we just do the tail loop. Compose new token. Okay, so this is sort of, like I said, when the Lexer says peek new token, maybe we have a new token ready already because we already composed it. But if we don't, we call this, and this is how we generate. This is the fundamental way that we generate the output for the parser. And this is sort of the main loop that I was talking about, where we don't really know what we're looking at, so we're iterating. We're looking at the next character. If it's a space, we just keep peeking. This, again, you could have a SIMD blast through spaces thing, but we don't have that. If it's end of file, right, tell the parser that. If it's a token that could start an identifier, make an identifier and return that. If it's a backtick, well, we do some things with backticks. We don't give the parser backtick as a separate token. We could. That's sort of, you could do it either way. The way we happen to do it, because backtick only goes on identifiers and keywords, we just give the parser the identifier or the keyword and just tell the parser that it's backticked. So that's how we handle backtick. If it's a dot, it could be a few things. It could be double dot. It could be this dot question mark that we don't actually support, but it's still in here. It could be, you're allowed to write 0.3 without saying 0.3. So if you do that, you might encounter a period as the first character of that number. And so if the second character is a digit, then we go make the number. Otherwise, we make a dot. All right. If it's something that starts a number, we call make number here. And then here, this is, like I said, a lot of tokens are just one ASCII character. So these, for example, are examples of that. Make one character token. So these are the simplest case. It's like I saw a parenthesis. There are no tokens in this language that are parenthesis followed by anything. So if you see a parenthesis, you just know what the next token is. Boom, it's a parenthesis. So that's the case for all of these. E2, what the hell is E2? This is something somebody else put in about directional whatever. I'm not a fan of entertaining weird Unicode stuff, but so like if you're in a language that goes left to right and you have some right to left in there or something, I guess this is in there. I don't know why we want that at top level. I assume Raphael put this in. I don't know. I don't know what it does, honestly. But there you go. That's what E2 does. All right. This is for directives usually, except we also do a hash bang at the beginning of the file. So we usually return hash as a token, but if there's an exclamation point, right? I'll skip ahead pretty fast, but you know, there's a lot of the same kind of stuff. Ampersand could be single ampersand, it could be double ampersand, it could be and equals. Oh, so we see the check for equals, right? So this is a convenience function that just says if you see an equals, it's token and equals, otherwise it's token and, right? Etc. So we do that for a bunch of these things that could be, you know, it could be rotate right or rotate right equals or greater equals depending on what we see, right? So this is again is pretty smooth brain code, but it's very obvious, easy to understand code. That's the thing, right? Is like, okay, if you see a greater than, well, what are the possible things it could be? It could be single greater than. It could be double greater than. It could be triple because we have a triple. And it could be any of those with an equal sign after it. So let's just do those. And so we do those. The end. And you know, there's a little more stuff, but it's all of that same general character. What's C2 though? Unicode non-breaking space. Yeah, great. So peak token is the thing the Lexer or the parser uses to ask what the next token is. This is a little bit of a messy factoring that we're probably going to want to refactor when we do the conversion. Set input from string. Okay, there's two places that we might want to get input from. There's from string or from file, right? Because very often we read a file and just use that as the input, but sometimes we already have a string in memory that we want to give you as the input, right? So for example, somebody says add build string, here's the string. We just parse that string to the Lexer. Now in both of these cases, they turn into the same thing because like I said, if you set from a file, we just load the file anyway, and then we treat it as a string. So these are really not that different from each other. And then I think we're at the end here. Show error context, we're probably not going to translate. But it's basically, this is another very smooth-brained function where when the compiler wants to output an error, we just load the frickin' file and count forward that many lines and then show the error. And there's a bunch of complication in here about highlighting the range of the identifier and that we want to highlight and stuff. None of this is really a lexical analysis task, actually. I think I put it in the Lexer because in theory, like the Lexer is already reading the file. So if you wanted to optimize that and not reread the whole file, this would kind of be the place that knew what the data was. But this is not part of what we're going to port because it's not generating tokens. And so really, we stop at line 1800, not line 2000. So that's good. That gets rid of about 10% of the file, actually. But that's it. That is all the things that we're going to do. I am going to make a chai latte. I think this stream is going to end in about 15-20 minutes. So I can go do some stuff, and then maybe we'll do this afternoon or evening where we start actually porting the code. I thought I was going to start this stream porting the code, but we did ranting and then just overview. So hopefully that overview was useful to people. Maybe it's not. I don't know. Are there questions about what we specifically just looked at? And by the way, for people for whom that might not have been clear, all that code that we just looked at is the actual shipping code in the compiler that, what just happened? My thing was not happy about. Oh, it came off. Now I have milk all over my hand. Good thing we're heating it up to kill my hand germs. All of that is the actual code that runs in this compiler that runs at good speed to Lex everybody's programs, right? So there's nothing, even though some of the code, like I said, could be faster, it's all at a totally fine, reasonable level. And in fact, this code is faster than probably, I mean, I haven't actually benchmarked it, but if you use a tool like Flex or whatever, this is probably a lot faster than what that would generate. Okay, questions people have. Does the Lexer work on the file that has been completely loaded? Yeah, that was my point, is we load the entire file so that we don't have to worry about complexity of each character, because like I said, you can load 300,000 copies of the file, so why not load one? And it's fast. I'm going to try putting the lid on the chai latte to see if it's quieter. It's a little bit quieter. Is SIMD parsing on or off in the current state? It is on. As the compiler ships, it is on. Let's verify that. Use SIMD 1. So, however, you know, we don't have SIMD everywhere that we could, right? So you see a character, and you call some function to consume the expected token from that single character, and you just do that for the whole file. Yeah, I mean that's why Lexers are so easy to write. Is it's very smooth brain. What it's doing, right? Is it's like what does this next character tell me the token is going to be? Okay, let's go do that token. Let's go do a string. Let's go do a number. Let's go do an identifier. And all of those things have clear rules about what they could be. And that is also what makes this a successful abstraction is, on the one hand, there is lots of fiddly stuff, like you saw the escape codes for strings or whatever. But on the other hand, the parser doesn't need to care about that once we give it a token and just say, here's a string, right? It's a very, very successful abstraction. What is going on with people today, dude? If you start thinking about what the previous token was, you've started writing a parser, not a Lexer. That is true. That is true. What is having the Lexer's library enable? I mean, we talked about this at the beginning of the stream, but yeah, tooling, for example. Like having things that match exactly. Do you have any syntactic sugar features that lex into the same parse tree? I mean, You mean Lex into the same stream of tokens? Or do you mean different stream of tokens that become the same parse tree? I mean, not really. Well, here strings is one of them, right? So you could write a string with double quotes, or you could write a string with here strings. And that becomes the same token, but it looks pretty different. Why do you need a scratch buffer for each token? I don't remember. That's what I was saying. Is I don't remember why I did it that way. I think it might be because like I might have at some point for strings or identifiers not allocated the result and just passed back, this is a string and the, you know, the name of the string is in the scratch buffer or whatever. But actually that wouldn't work for strings because the scratch buffer is too small. Yeah, I honestly don't remember, and I don't think it's really a good place for it. So I would like to factor it out. Did I take any ideas or code from the LERP language? Not really any ideas, but this Lexer actually started life as that Lexer. Because Lexers are all very similar to each other. You just copy one and then you just change what it does, right? And so that, again, that was the idea for part of the utility of this is that once this is ported, people using this language can just copy it and change it a little bit. Like, oh, I don't want my identifiers to be like that. I want them to be like this. And you just change that function, and then there you go. Dude, the froth is insane right now. Are we going to test the library somehow to prevent it diverging from the compiler? Maybe. We'll think about that later. Like, the first step is just to have something, right? So website still says maybe someday I will come back to it. Yeah, well, I think the way we came back to it was by doing this instead of that. I think that's what it is. Any other questions on this? How does Lexer handle cases where the token is dependent on the parse state? It doesn't. I just don't allow that. Yeah. Like, that's not... Like, that's a thing that people know about because C did it. The thing is, it's not really a very good thing to do because, for example, tools have a harder time once you do that. But also it complicates your parsing code. It prevents parallelism, right? It causes all sorts of problems. And the thing is, you don't really get much for it, right? The reason that happens in C is because of two things put together. One is that type defs turn, you know, identifiers into type names, and type names are a strictly different thing in the grammar from other things, right? And it's honestly not that big of a change to get around that problem. Like, you're not buying yourself very much by doing things that way. And so most modern languages just don't have that problem, like most that are any good. All Lexer is doing is transforming one representation of your code to another one with the goal that the new representation is easier to feed to the parser. Yes, although it's not only doing that. That is most of what it's doing. It's also got a little bit of a job as a user interface, right? Like, you know, we did a little bit of error reporting in the middle of our Lexer because, wow, this got really hot. I guess with the lid on, I mean, it makes sense. Maybe I should froth with the lid on. From now on. Do the nodes in the abstract syntax tree contain the corresponding tokens? No. I discard the tokens. Like I was showing in the beginning, there's only a ring buffer of 8 tokens, so I don't keep them around. What happens is the parser takes the information it wants and copies it off, and then the token goes away. It feels so far the lexing is quite tied to the syntax of the language. Is this going to be reflected in the end result? Are you going to remove those assumptions? No, I mean, it's not really that tied to the syntax. Because tokens are not really, they're like the molecules of syntax, like I was saying, right? So like syntax is more like what you do when you see individual tokens. Now, yes, it's true that there are some tokens in here that you might not have. Like a lot of languages don't have plus equals as a token, right? But like, it's just really easy to then take out plus equals, right? And then if you have some other compound thing, you put that in. Like, it's just not that big of a deal at this level, right? And so that's why I was saying, so the syntax of this language is quite different from the syntax of that language LERP that I did in the game developer articles. But I started with that Lexer and just changed it. Like, it's not that big of a deal. The structure of the Lexer is pretty much the same, let's put it that way, regardless of the details. Do you convert the AST into x64 assembly code and compile that? Do you mean as text? No. No. Do you need to do error reporting for the blatant syntax errors in the Lexer, or can you defer all error reporting to the parser? Well, it's probably simpler to do it in the Lexer. For example, we have this \u in a string, and like I said, it's followed by 2, 4, or 8 numeric characters. If you have 7 hex characters after a \u, that's just wrong. If you wanted to report that from the parser, the Lexer would have to somehow tell the parser to report this error and pass to it all the information it needs to accurately report the error. Like how many characters were parsed versus how many were expected and all that, or were lexed and versus how many were expected and whatever. And like, that's just, why? Why would you do that, right? Whereas if you can just report from the Lexer, you have all the information right there. The Lexer knows about 2, 4, or 8 characters. The parser doesn't need to. That's part of the abstraction line that you're drawing. And so to bring that back just to report errors is a little bit weird. What is the construct that uses the 3 token look ahead? I think it's when we're starting a function declaration. because there's like an open parenthesis. Like, okay, you see some tokens, and the first one is an open parenthesis, right? Let's do this. The second one is a variable name, x, right? What could that be? It could be x plus 5, right? It could be x of 7, right? Because you can put, like, parentheses are just used for grouping, right? Or it could be x int y float to string dot dot dot, right? It could be either of these things. And when you see open paren and x, you still don't know. So you need a third character. If it's a colon, then we know it's a procedure declaration. Otherwise, it's an expression, a general expression. But this is all parsing is, by the way. So in the same way that lexing and parsing are kind of the same thing at two slightly different levels of abstraction, right? So in lexing, you're spinning over the characters and doing very smooth-brained stuff. I hope that wasn't too loud. Doing very smooth-brained stuff to figure out the tokens. In parsing, you're looking at the tokens and doing very smooth-brained stuff to figure out the syntax tree. That's all. So it's literally, instead of writing all this shift, reduce, crazy Bison parser situation, you just do the thing. It's like not that hard. How do Lexers work when there is an error? So the way this whole system works is the parser will stop when an error is reported, and the parser asks the Lexer for tokens. So the parser will just stop asking the Lexer for tokens after you hit an error. All right. How do you work with the grammar over time? Do you have a list of rules that you edit? No, you just literally edit the code. That whole thing about having a list of grammar rules is really only useful when analyzing a grammar. It's not that good for implementing a grammar, right? I mean, unless, or as documentation, like if you wanted to document, here are the things we parse, right? I don't do it that way because I don't care about that. How about the case where the token is just invalid? Is that some sort of error token? No, I mean, we just report an error, and like I said, the Lexer knows to stop. There are other invalid tokens, like, you know, if you see ASCII 127, that's probably not a printable character. I don't know. It's probably not one that we use. I don't remember. But there certainly are ASCII characters that we don't use. Like we don't actually use, oh no, that's not true. I don't know. There are some. So, you know, if you hit that, the Lexer will just say that's not a valid token. Or the parser will say, you know, we expected something that starts a general expression, but we got this weird character. Are you planning to report all the errors at once in a file? No, I mean, the way we do it right now is we'll report a maximum of one parse error per file. And the reason is because once you hit an error, you're not necessarily parsing correctly after that. And you can generate a lot more errors that are spurious and don't have meaning to the user, right? So C++ compilers do this all the time. Like you're using Visual Studio and you compile your C++ program and you get like 57 errors, and experienced users just scroll up to the first one and fix it and recompile, because the 56 after that are all trash, right? And that's why all the fucking other shit that Microsoft added to the compile, like they have this like error report window instead of just giving you the output, and then they sort the error report by some nonsense criterion that puts things out of order, and then you can't debug anything at all because you get 57 errors and the one that's actually the real error is in the middle somewhere, and you're just like, what the fuck is this? So you always have to turn that off. The G++ compiler just reports the first error, yes. But many compilers through history have had the same kind of bad behavior as Visual Studio. I think Clang just spews errors as well, right? But yeah, the thing is, if a parse error is in a different file, then we know we haven't desynced from the correct parse when we hit that error. So we will, if you make 3 parse errors in 3 separate files, we will report all of those. Okay. Well, there's only like 5 minutes left in the stream, but we're just going to go start. We're just going to start converting it, and it's going to be very, very smooth brain. We're going to start just by making it compile and run as is, and then we're going to go over it and question some of these implementation decisions, like, like, do we want this max token length in the scratch buffer, or all that kind of thing. Okay. This is going to be enum. See, this is I'm actually going to make this an S16 for now. And the reason is because we have -1 and then all these positive numbers, right? I think we want to change the range of numbers to not, like, we could probably fit them all under 256 if we want, but that's still more than S8. We could make end of file not be -1. That might be a good idea. How do you handle backslash in identifiers? We can go over that when we're converting the loop. But yeah, they're removed in the Lexer. Like the Lexer at the end produces just the name of the identifier, regardless of how it's written. That's the point. That's its job. That is its job. So I'm hitting a dilemma even worse than the dilemma in BioShock. Maybe I should clean some of this stuff up in the actual compiler first, like the scratch buffer and things, because then if we just do this conversion, we'll convert all those improvements. Or maybe not. You know what? We're gonna do it this way, and maybe we can backport. Anyway, this is just a very, very smooth brain conversion. The reason I want to do it this way is because I like this language more than C++, and I would just rather think about and solve problems in this language. And in fact, I would rather structure things like, I think my problem solving is better in the new language, and so I probably will come up with better solutions to things and just be happier, and then we can backport. Wait, I say these must be synced? That's not true, right? We have code node.kind, but that's not, yeah. I must have written that back when I was thinking we would export tokens, and we don't do that. Okay. This is a node flag. You know what? All this token underscore can go away. Talking like docking. Okay. So just going to do that. We're going to do this. Token string is a struct. Again, right now, we're just not going to think that hard. We're going to get it compiling and running. And then later, we can go through and like question these design decisions more seriously. All this stuff, we don't have constructors, so we don't need to talk about constructors. Okay. So we have a union. Well, yeah, I have a feeling we're going to change a lot of this. Going to change a lot. Okay. So those are our possible things. We've got value flags. We've got ident is backticked. That's really stupid. All right. So token string. Oh. Yeah. That was me goofing. Expect a lot of goofs like that. All right, you know what? It's 11 a.m. my time, so we're just going to pause here. What we're going to do on the next stream is just continue doing this and it's probably not going to be too exciting, honestly. Actually, let's go. Remember, we said we don't need this stuff, the error context stuff. So all we really need is 2053 lines, and we are on line yeah, I said token and then token up here. Hold on. We're going to put this back to token type. So we are at or around 153 out of 2053. So we're like less than 10% in the initial pass, but that's fine. It was just a few minutes. All right, thanks everyone for coming by. We will do another stream later on. Have a good day. I hope you're having a good weekend. Weather has been amazing, both in Florida and here. So you can't get away from the good weather. And see you next time. Maybe I'll be this afternoon, maybe it'll be tonight, maybe it'll be tomorrow morning. I can't predict.